Hello, and in this video we're going to continue our discussion of average rate of change by introducing this concept of a difference quotient. So recall, in the past video, we defined the average rate of change of a function f on an interval a comma b to be equal to f of b minus f of a divided by b minus a. So what is it exactly is this number capital A? So if we have some function on where you have an interval of interest, say a comma b. So this is going to be f of a, this is going to be f of b, and we realize that this number af of ab is simply the slope of the line that passes through these 2 points. So this is the slope of the secant line. So in this video, we're going to slightly redefine this in terms of other variables. So let us consider the same exact picture. So here's going to be our function f, and I'm going to define this point to be x, and we're going to have another point in the future. So if this is x, then that means this point right here is going to be f of x. And let us assume that this next point is going to be h distance in front or behind of x. So for example, if this x is 5 and h is 2, then that means this next point is 7. But in general, if that distance is h, then that means this point is going to be x plus h. So if that is true, then that means this point is going to be f of whatever that value is. So again, the average rate of change is going to be the slope of the line that passes through these 2 points. But instead, I'm not talking about A and B. Now I'm talking about how things are changing with respect to this point and a point that's in the future or in the past of that point. All right, so what does that mean? So that means the average rate of change of this function on the interval AB is equivalent to the average rate of change of f on the interval x comma x plus h. So that's going to be equal to f of x plus h. So that's going to be this second y value minus the first y value, which is going to be f of x, divided by the x value that corresponds to the second, which is x plus h, minus the x value that corresponds to the first, which is just x. So notice that some things do simplify here, namely these x's in the bottom. So we get that the average rate of change of the function on the interval a comma b is equal to f of x plus h minus f of x, all divided by h. And notice that there is no ab on this interval. There is an x and an x plus h, but that's a little bit messy. So we define a new function, and I'm going to call it d of f of x. Actually, d of h of x. And this is going to be equal to f of x plus h minus f of x, all divided by h. And this is what I'm going to call the difference quotient. And this is for our function f, but I'm not going to write it here. All right, so what does that mean? So the difference quotient is practically the same thing as an antiderivative, except it's comparing a point x to a point that's h distance from it. So let us demonstrate this with a couple examples. Example 1. Let f of x be equal to x squared. So what is the difference quotient for this function f? So by definition, dh of x is going to be equal to f of x plus h minus f of x divided by h. So f of x plus h just means plug x plus h into this function. So we're just going to have x plus h squared minus that function x squared, all divided by h. So I'm going to expand the numerator of this function. So x plus h squared will FOIL into x squared plus 2xh plus h squared minus x squared all over h. So we can note here that these x squareds do eliminate. And this is going to be equal to 2xh plus h squared all divided by h. From here we have an h that is common with the top terms. And we can algebraically cancel these. And we're left with this is equal to 2x plus h. So this is the difference quotient dh of x for f of x is equal to x squared. And in the next video, we'll sort of demonstrate why this is actually useful. Let's do another example. Let f of x be equal to x cubed. So let us calculate the difference quotient for this. So the difference quotient of x is going to be equal to, again, f of x plus h. So I'm going to plug x plus h into this function, minus that function itself, all divided by h. This top term I can expand into x cubed plus 3x squared h plus 3xh squared plus h cubed. And if that's not obvious, then you can multiply together x plus h times x plus h times x plus h, FOIL the first two, and then FOIL that result into that last x plus h. And you'll realize that it will come out to this. All divided by h. Again, notice that these x cubes will eliminate. And we're going to be left with 3x squared h plus 3xh squared plus h cubed all over h. Again, we have an h that is in common with the top, so I can factor it out. Notice h will cancel. And we're left with 3x squared plus 3xh plus h squared. And this is the difference quotient for the function f of x is equal to x cubed. So the first observation is this. At least for these two examples, h always seems to cancel, or I'm going to say, or be removed from the bottom. Also, in particular to these functions, there's another observation that we're going to take advantage of. So if I want to find the difference quotient for, say, f of x is equal to x to the n, where n is just some number, what do we have here? Well, there is possibly a pattern that may be rising here. Notice that x squared has a value of 2x, and x cubed has this 3x squared term in the front. And you may even want to try it on yourself, that the dhx is going to be equal to 4x cubed plus some stuff if you let f be equal to x to the fourth. Namely, the exponent comes down in the front and the exponent drops by 1. So if that is true, which we'll verify later, then that means dh of x is going to be equal to n times x to the n minus 1. And notice that all these terms left is going to have an h term in it. So I can always factor it out. And I'm going to be left with some function of x and h. And this is going to be a useful identity to prove another identity that we will take advantage of later. But overall, what is this that we're talking about here? So it just shares a very close connection to the average rate of change, which recall again, f of b minus f of a over b minus a. And there is no significant difference between these two functions, except that for the average rate of change, we're only talking about 2 points, whereas the difference quotient, we're only talking about one particular point with respect to another point in the future. So overall, it's the same exact thing, but we're going to take advantage of this second one in the next video.